Now that we have seen Priscilla and Scotty in action and have related that to real P and S earthquake waves and how the lag time between when the P wave arrives and the S wave arrives can be used to get a sense of the distance, we're going to make this even more accurate and specific. So the Earth Science Reference Table has a page on 11 that shows how mathematically we can use the lag time to get an exact distance of where that epicenter is from our recording station or our seismograph station. So one important thing is to remember that the P and the S waves don't speed up or slow down in their journey as long as they're staying in the same general layer of the Earth. So the P wave is not getting ahead of Scotty because she's speeding up, or Scotty is not slowing down, that's why he falls behind. They're going the same speed the whole time, and it's just that Priscilla is so much faster than Scotty, or the P wave is so much faster than the S wave. So we're going to see how this graph works. The x-axis here is going to be the epicenter distance, and that's the distance of our run. So we can see that the epicenter's distances are 1, 2, 3, 4, and so on, but that's not 1 kilometer or 2 kilometers and so on. It's 1 times 10 to the 3 or 2 times 10 to the 3 and so on. And since 10 to the third power is 1,000, this is really 1 times 1,000 or 1,000. 2 times 1,000 is 2,000, 3,000, and 4,000, and so on. Since every box here also represents a distance, we need to figure out what each one is. And there are 5 boxes here between 1 and 2, and we know this is a 1,000 kilometer difference, so 1,000 divided by these 5 boxes gives us 200 kilometers per box, or 200 per tick mark here. So there's our epicenter distance. Now we're going to go to the y-axis over here, and that's going to tell us the travel time, or how many minutes and seconds it takes each wave to complete the race. So we're going to start with an epicenter distance of 0, meaning the seismograph station is right where the earthquake is. So now, if this is the case, there is no distance for the P wave to get ahead. It was like the last race between Priscilla and Scotty. There was just no distance for her to do any separation. So they're going to both arrive at the seismograph station at the same time. But what happens if there is some distance for them to separate and if the lag time is not 0? So we're going to do an example of 1,000 kilometers here. Now in this case, there is time and distance for the P wave to get ahead of the S wave. And there is a gap between them, and you can see this is a gap between them on the travel time graph. So we can see it takes the P wave about 2 minutes to travel this 1,000 kilometers. It takes the S wave around 4 minutes. So if the difference then between the 4 and the 2 minutes is going to be 2, we know our lag time is about 2 minutes. So if the S wave comes in 2 minutes after the P wave, then that epicenter is about 1,000 kilometers from the recording station or seismograph station. And when you use your reference table, you're going to want to keep track of this by using this idea, this gap between when the P wave came in and the S wave came in. All right, let's do a longer race now. We're going to do a 9,000 kilometer race. So now, since the distance is a lot farther, there's going to be much more distance for Priscilla or the P wave to get ahead. And you're going to see separation here now. Okay, so like that second to last race where Scotty came in so far in back of Priscilla, here is that comparison. So a long race, we're going to have a long separation, and now you can see there's a big lag time or a big gap between the two. So now we can see that it takes the P wave a little over 12 minutes to go this 9,000 kilometers, and that's going to be here. And now, how many seconds is that going to be? Well, if we have a minute divided up amongst 3 boxes, we have 60 seconds here divided by 3 gives us 20 seconds per box or tick mark. So this is going to be about 12 minutes and 20 seconds. Now for the S wave over here, to go that same distance, it takes actually 22 minutes and 20 seconds. So now we have a lag time of about 10 minutes here. All right, so here was a 2-minute lag time. Here now at 9,000 is going to be 10. Much different. So you have to keep in mind the gap between where the P and the S wave are going to be arriving in order to get a sense of that distance. Now, in class and when you're doing your work, you're going to be using scrap paper, and we're going to demonstrate how to do that to measure this lag time. So if you put a piece of scrap paper and you marked where the start and end of it is, you can drag your scrap paper to your y-axis and you're going to be able to see that gap over here is 10 minutes. So that's going to be a nice simple way of determining lag time, and this is what the seismologists do. They know the lag time by recording when the P wave and the S wave arrives, and that's how they get that difference which they use to figure out the distance. So we're going to see this as an example. Let's imagine that scientists know, or the seismologists know, that there was a lag time of 5 minutes and 40 seconds between the 2 waves. So we can plot that here as 5 minutes and 20, then the next lineup is 5 minutes and 40, because everyone's 20 seconds. Now if we drag this, we find where that gap matches our line, or our 2 dots on our scrap paper. And now we can clearly see that that's going to be about 4,000 kilometers away. So now you're really ready to do this earthquake analysis, and we're going to be getting a lot of practice with that in class. So we are warmed up and ready to go.